Continuing in 12.1. Example 3. A turtle walks with a constant speed in a counterclockwise direction on a circular track of radius 4 feet centered at the origin. So I have counterclockwise, it says. Well, that was a pretty good circle. Starting from the point 4, 0. So this is the starting point. The turtle completes the lap in 30 minutes. One lap, 30 minutes. Okay. Find a parametric description of the path of the turtle at any time t is greater than or equal to 0, where t is measured in minutes. All right, so we just did example 2, which is very similar to it. So all I need to do is say is that x is equal to 4 cosine of some bt, and y is equal to 4 sine of some bt. And now I just got to figure out what I need to put in there for this to work. Now he makes it all the way around in 30 minutes, so that's going to be my boundaries. So I need 30b to be 2 pi, or once around, which means that b would be pi over 15 radians per minute. So therefore the parametric equation just needs to be x equals 4 cosine of pi t over 15 and y equals 4 sine of pi t over 15 for 0 less than or equal to t less than or equal to 30. And if you plugged in numbers, you would find out that that is working. Okay, example 4. Parametric lines. Express the curve described by the equations x equals x sub 0 plus at and y equals y sub 0 plus bt in the form of y equals a function of x. Assume that y sub 0, x sub 0, a and b are constants, and a cannot equal 0, and my t is from negative infinity to infinity. All right. So all I really need to do is eliminate the parameter. That's what they're telling me to do. They said y equals a function of x. So let's take the x equation and let's solve it for t. So that would be x minus x sub 0 over a is equal to t. So now let's go to the y equation, and that would be y sub 0 plus b times x minus x sub 0 over, oops, that's supposed to be an a. If I try to clean this up a little bit, I could bring that y sub 0 over so that we would recognize this, and this is going to be b over a times x minus x sub 0. So this describes a line that has a slope of b over a and goes through the point x sub 0, y sub 0. And they've done an illustration in the book. They said x equals 2 plus 3t and y equals 1 plus t would meet the qualifications. It would go through the point 2, 1 when t was 0 and would have a slope of 1/3. So that would be one such equation that would work. But they also made a point of saying, you know, we don't have to really do that. We could have written x equals negative 1 plus 6t and y equals 2t. And that would be, when t is 0, I would have negative 1, 0 at t is 0. And this slope, yes, and that would be fine the way that one works too. Its slope is still 1/3. So there's a variety of answers you can do with that. It's not unique. Okay, so we're ready for example 5. A common task, particularly in upcoming chapters, is to parameterize the curves given either by Cartesian equations or by graphs. Find a parametric representation of the following curves. Okay, part A, the segment of the parabola 9 minus x squared for x's between -1 and 3. All right, the easiest way to do this is just to start out with x and say let x be t, and then y would be 9 minus t squared. And put t between -1 and 3. That's the easy way. I could adjust this or anything I want. Again, it's not unique. I could make this as x equals 1 minus t, which means that y would be 9 minus 1 minus t squared. And now if that's the case, instead of going from -1 to 3, it'd be moving from -2 to 2, because it's been shifted over 1. And the biggest problem here, they trace the parabola from right to left, while the original equations trace the curve from left to right. So it's a little weird the way it happens, but it will draw the picture. We usually draw from left to right. The first one graphs it the other way around. So, whichever way you want to go, but you want to have the arrows run in the right direction. Okay, so you got to be very careful on this. This one, when you graph these, you should get the curve that goes like this and hits right here at 3, I believe. But the graph that we're doing is heading this direction. That would be this one right here. But if you do the second one that I wrote for you, yes, it does give you the same exact picture, except that graph is going to head this way. So since when we graph rectangularly, we graph from left to right, then you need to write the parametric one that's going to go from left to right. Part B. Part B wants us to do x equals y minus 5 squared plus the square root of y and turn it into parametrics. Okay, don't make this one tough. I would let the y equal t, and then the x would equal t minus 5 squared plus square root of t. Now when you do the intervals on this one, you can only pick things from 0 to infinity, because you can't put stuff in there that's going to make the square root come out negative. So this really only works from 0 to infinity. And then part C, the piecewise linear path that connects this one to Q to R in that order, where the parameter varies over the interval 0 to 2, which means 0 is less than or equal to t less than or equal to 2. Okay, this would be 2 line segments, so it's piecewise, so we're going to have 2 parts to it, so it's going to have 2 different sets of parametric curves. And we're going to go back to what I used in number 4. X is equal to x sub 0 plus at, y is equal to y sub 0 plus bt. And PQ originates at -2, 0 and unfolds to the positive x direction. It's going to have a slope. If I calculate the slope on that of 3/2. Okay, so I know what the slope is, which means the 3 is the part that goes with the y, and the 2 is the part that goes with the x, and since it starts at -2, -2 plus 2t. So your 3/2 is appearing here and here, and then your point, -2, 0. And this works when you pick t's between 0 and 1. Now check the endpoints to make sure. If you stick in 0, you do get -2, 0. If you stick in 1, you get 0, 3. That's what we're trying to have. So there's the first piece. Okay, now I have to go from Q to R. This was P to Q. Q to R, what's the slope there? The slope is going to be 3 over -4 or -3/4. Remember, the equations are not unique, so there's several ways of writing it. And this one originates at 0, 3 and unfolds, and it has to go to 4, 0. So, what you got to remember is that the 0, 3 happens when t is 1, because that's what we're picking up. So when t is 1, I'm supposed to get 0 for the x and 3 for the y. So I already know that I have to have a slope. Let's put the let's make the 4 the positive one, and then the negative 3 for the y. So I have my negative 3/4 slope. Now when I stick in 1 for t, I'm supposed to get 0, which means I need a negative 4 here to make that work. If I stick in 1 for t in the y value, I'm supposed to get 3. I'm going to get negative 3, so I need a 6 here to make that work. Now just check, because this is going to now work for 1 is less than t is less than 2. Let's check the 2. Put a 2 in and you get negative 4 plus 8 is 4, so that's the r part, the x for the r. And then stick 2 in the y equation and get 6 minus 6 is 0, so I am getting 4, 0 for my terminal point. So that's the second piece to that graph. And they have graphed them in the textbook for you, but they're just two straight lines, and they have their arrows on them. So the one, just plot your dots. They were negative 2, 0, 0, 3, and 4, 0. So this one went like this with an arrow here, and this one went like this, arrow going that way. So this was at t equals 0, this was at t equals 1, this was at t equals 2. Okay, that finishes example 5.